Let's discuss how unit analysis is being done and how is it useful for science. The fundamental or base quantities that are used in physical descriptions are called dimensions. For example, length, mass, and time are dimensions. You could measure the distance between 2 points and express it in units of meters, centimeters, or feet, but the quantity would still have the dimension of length. So dimensions provide procedures by which the consistency of equations may be checked. In practice, it is very convenient to use specific units such as meters, kilograms, or seconds. Take a look at this chart that I'm trying to make. I have a quantity on one side and units on the other side. So suppose we have a quantity that measures mass of something. So the unit for that, it would be, for example, kilogram. For quantity that measures the time, the unit will be seconds. For length, it would be meters. Like another quantity, for example, area, the unit would be meter square. We'll discuss this mixed units a little bit later. Such units can be treated as algebraic quantities and be cancelled with each other. So using units to check equations is called unit analysis. That shows consistency of units and whether an equation is dimensionally correct or not. So let's try an example. Before we go ahead and do our first example, let me just give you some more quantities with their dimensions, like volume is measured in cubic meters, velocity. We put like we denote the velocity with the lowercase v. It's meters per second, and acceleration, which we denote with a or g. So it's measured meters per second squared. Now let's try this example here. Example. Suppose we have an equation v equals v naught plus at. So if you look at this expression, v, I said we're measuring velocity with v, or we're denoting actually velocity with v, and then when we put a little subscript in physics, that means it's like if it's naught, like a 0, it means it's an initial velocity, or whatever we decide together to or agree together to make of the v naught, but usually v naught is the initial velocity. So v and v naught are notations of the same quantity. And then a is the acceleration, t is the time. So let me just put that in here. Time in here usually is denoted with the lowercase t. Now let's make a dimensional analysis or as unit analysis. So all we need to do to check whether on the left side of this equation and the right side of the equation, the units are the same. So we know already for the left side, the units for the velocity is meters per second. On the right side, we do have for the v naught, it's still velocity, meters per second, plus for acceleration, we have a meters per second square, and for time, we have, I'm going to put this cross as a time, and then I put the second in here. So as I said earlier, we can cancel some of them out. So this would be one of the seconds will be canceled. So I have a meters per second plus meters per second. So imagine if you're adding one apple to another apple, your result is 2 apples still. So if I'm adding 1 meters per second, 1 meters per second, the result is gonna be meters per second as well. So on the right side, I have meters per second. On the left side, I have meters per second. So which means this expression is dimensionally correct. Okay, so we can put the check mark. And we can try another example. Okay, so let's see like an expression x equals v over 2a. Well, you can stop the video right at this moment and try to do it on your own. And when you finish, hit play again and check your result. Now, let's see. On the left side, x is the notation for length. So let me put here x. So it's measured in meters equals, I have this fraction line here. For the velocity, I'm going to put the meters per second over 2 times acceleration is meters per second square. This, when you do dimensional analysis, you don't really need to care about the numbers. It's all about dimensions. I just put in here to emphasize that the numbers do not make any difference in unit analysis. So let's do this division. I can do meters per second, the top, and division I can make multiplied and over the bottom fraction flipped. So that would be second square over 1. So meter and meter will cancel, second and one of the seconds will cancel, and I will end up having second. So which is dimensionally is not correct because I end up having meter here equals second here, which is not correct. Dimensionally not correct. So therefore this equation is not correct. But I want you to be very careful here. The unit analysis will tell you that this equation dimensionally is not correct or correct. It doesn't mean that the equation is physically correct. So let me show you an example real quick. So suppose that you have an equation that x equals at squared. So we know that, let's do the dimensional analysis for this one. And then we have x is measured in meters. So I'm going to put this equation sign and ask whether it's going to equal dimensionally on the other side or not. Acceleration is measured in meters per second square. Time is measured in seconds. And there is a square on the top. So this square makes it second square. So as you can see, the second squares cancel out. We end up having meter equals meter, left side and the right side. So then we can claim, yes, this is dimensionally correct. But as we will learn later in next chapter, it is not physically correct. Not physically correct. In reality, physically correct expression would be x, for example, equals 1/2 at squared. This fraction of 1/2 has no dimensions. It is an exact dimensionless number. So unit analysis cannot tell you if an equation is physically correct, only whether or not it is dimensionally consistent.